today we're going to do more linked lists, and we're going to look at inserting more and deletion if we get time for deletion. Just a few announcements before we start. So today we've got the assignment 2 live stream. Hands up who's looked at the assignment or started the assignment already. Okay, cool. Now, there's some parts of the assignment right now that if you don't know linked lists, that's going to be a bit hard for you to do. But there's some parts of the first stages where that's going to be okay. So you can get started now. Yeah, so we've got the live stream at 4:30. So you can come to the YouTube link. There's a link from the assignment spec as well. And there'll also be a recording available. But if you turn up to the live stream, then you can ask questions in the live chat. So that's the benefit of that. The due date is Friday, week 10, 5 p.m. Don't leave it to the last minute, of course. I've said that a million times. The other thing I wanted to talk about was, we've seen a pattern of many students using a lot of ChatGPT. So I just want to warn you, just be very careful in your assignment 2, because if one person uses ChatGPT to generate some code for a function, you can imagine out of 1,000 other students who might have used ChatGPT to generate those functions, you might end up with the same code, which will get flagged for plagiarism, even if we can't look at it and see that's obviously from ChatGPT. So there's a few ways you can get caught out. But I guess the biggest problem is, you're not gonna have ChatGPT in the final exam. So it's better that you don't over rely on it. Okay, so that's just a little bit of a warning. And that goes for labs too, by the way. You need to be able to, the exam's coming up in a few weeks, so you've got to get used to debugging and coding without over reliance on things you can't use in the exam. Okay, and if you are a bit behind or you need more help and that's why you're doing it, or even if you're not doing it and you want to go to revision sessions, there are some on this week. Wednesday 12 to 2, Friday 2 to 4. You can sign up. You can vote for your topics. I think the votes are still open. So don't forget to make use of all the help. We've always got help sessions too. Okay, so today, last lecture you might recall we did some linked lists. We did some basics, explained what they were, printed a list, and we inserted nodes at the beginning of the list. So today we're going to look at, we'll do a bit of a recap. We'll look at inserting at the tail or just anywhere within the list. And if we get time, we'll do some linked list deletion. All right, anything we don't finish today, we'll finish on Thursday. As usual, we've got a link to the week 8 live lecture code. But to start with, I want to do a Kahoot just to see how everyone's going with malloc and linked lists before because it's really important you understand the basics before we go on and do something more difficult. So everyone, let's do a quick Kahoot. That will hopefully get our brains going too. Oops, that's not what I'm looking for. So I think this is malloc and very basics of linked lists. Oh. No players so far. Okay, here they come. Oh, yeah. Is it? Oh. That's not very loud. All right, is there anyone still trying to join in the room or at home? I'll give her another minute to wake up and a little bit and join. Okay, let's go. I'll start now. Actually, look, some of the other answers are technically right, you know. The heap is still RAM and memory, but most specifically, it's on the heap. It's definitely not on the stack. The stack's where our local variables are stored, and that's all managed automatically. Heap is the memory we get when we do malloc. Okay. So you might feel ripped off if you said memory or RAM. Okay. Okay, so yeah, memory can be allocated dynamically at runtime as needed. So while your code is running, you can malloc more and more memory as you need it. You don't have to know in advance how much memory you're going to need. And the memory you allocate on the heap persists after your function call has returned. So if I've got local variables in a function, what happens when the function finishes? They live on the stack, they get popped off the stack. They're not there anymore. They don't exist. That memory gets used for something else. So heap allows us to have memory that still exists, still holds all of our variables once our function finishes. Yeah, the lower address, I just threw that in to confuse people. And the heap doesn't automate the allocation and deallocation of memory. That's what the stack does. All right. Okay, lively bison. Okay, very good. Most people have that. Yeah, don't forget, yeah, you need the size of the thing multiplied by how many things you want. And what are the, yeah. All right. The rest just all have one slight sort of mistake. All right, someone said on the last slide, wasn't it 10? Did I have the number 10 instead of 5? I'll go back and check. All right, yeah, free wasn't called. Okay, we didn't call free. Probably if you ran your program, if you compiled it and ran it, you'd think it worked fine, and it probably would. But if we ran it with DCC minus leak check, it'd tell us we've got a memory leak. So in this course, we want you to do a free for every malloc, and in assignment 2, we will check that. Right. Okay, cool. Yep, that's correct. You have to manually free the memory. Yeah, sometimes people think the memory is lost forever. That's not true. It's just while your program's running, you're wasting memory. And if you keep doing that, you might run out. It'll all get restored and be useful on your actual computer once your program finishes. Okay. This is cruel, really. They all look so similar. I hope one of them's right. Wow, most people got it. And it's also cruel because the colours get shuffled around so that it was hard to see which one you're going to pick. But let's have a look. All right, this one here is missing the star. So this has to be a pointer to another node. Okay, for it to be a linked list. And actually, yeah, A is problematic, but we won't talk about it too much. Yeah, B was the right one. Why is C wrong? Yeah, it has to be a pointer to another thing of the same type. So a pointer to another struct node. Down here, that's just pretty wrong. Okay. Oh, free typing this time. I don't know. Okay, fair enough. Yep, so if you want to know the size of your struct node, this means size in bytes. Don't calculate it yourself. Use the size of function and say size of struct node. All right? Okay. Okay, yep. this is good, and a lot of people got it, so that's great. Blue, remember we need that star. New node has to be a pointer. Okay, last question coming up. How much time did I give for this question? Oh, 30. Okay. No, the counter that I was looking at here was on a different spot. I was getting confused. It's all right. Okay, yep, this is an empty linked list. Struct node star head is null. There's no data in the list, so the address that it's pointing to, there's no address to point to the first piece of data. Okay? All right. Let's see who won. And yeah, if you're in the room and you came first, second, third, fourth or fifth, put your hand up. Well done. Do we have Wonderhawk, Amusing Bobcat, or Charming Bear? Ah, awesome. Anyone else? Okay. All the people who came fourth and fifth who I missed. If you're in here, put your hand up as well. Okay. Let's get that music off. Okay. I think people did really well on that, considering you've only had sort of one lecture on it. And I didn't do a recap first. So I'm just going to quickly do a bit more of a recap on linked lists. So please pay attention, because if you don't understand these basics, it's going to be impossible to understand how to delete something from a list or insert something at the tail of a list. So remember, these are the important types that we'll be working with. Right? We've got a linked list. Our linked list variable is just a pointer to some kind of node. And the node that we've got and that we'll be using for a little bit is, we're just going to work with a struct like this for a while, has one int and then a pointer to the next struct. Later on, or if you've already looked at the assignment, you'll see you can have any type of data in here. It doesn't have to be one int, but for now, we just want to keep it simple to learn the linked list mechanics, which isn't simple itself. So it's a bit like a scavenger hunt. We've only got a variable that keeps track of this first chunk of data. So it'll know the address of the first node. And the first node has a value in it, but the first node also has the address of the next node in that next field. Shh. Sorry. And yeah, this next node has the value 17, but it has the address of the data in the next node, right? And the next node has the address of the data in the next node. When we get to this node here, we've got 5 as the data and we've got null as the next node. That's saying we're at the end of the list. There is no next node, okay? That's how we can tell when we've reached the end. If we've got an address in this node that's not null, we know that there's another node after it in the list. Okay, are there any questions about how that kind of works? Yep.
How does the linked list know the address when you haven't given it the address?
Well, that's the thing. When we start off, we've got no information and we've got an empty linked list and we've got null in it. There's no data, it doesn't know any addresses. But then every time we do a malloc, to create all of these nodes. And when we do a malloc, that gives us back the address.
Oh, so the malloc automatically gives it, so you don't have
So the malloc gives us the address, then we have that address, and that's how we can connect it all up. Yep. Okay, so let's have a look. And this is how we typically visualize our lists, right? I've got some kind of variable that stores the address at the beginning of the list or the first node in the list. We often call it head. It could be first, it could be list. It's just a variable name. So we're saying this struct is at address 28. Then this struct has the value 13 and it's saying the next struct is at address 80, etc. Okay, so imagine that these at the top, these are just fake addresses I've made up. But each node connects to the next node. All right, and because of that, we can't do what we do with arrays, like say, I want to go straight to index 99. We would have to start at the beginning and have a loop and go through and count our way up and work out when we looked through 99 nodes. Okay. So here, let's just revise building some sort of linked list. We're starting with an empty linked list. There's no address of any node because there are no nodes yet. So the head is equal to null. Then this is where we can do a malloc. And we wrote a nice function that can do this for us, but this is kind of the raw code. We can do a malloc to create a chunk of memory to store a node in. Then we can set the data inside it, because remember, when we've got a pointer to a struct, we use an arrow. So I can go and set the data field to 21. Now, because this is just one node and there's no other nodes to connect it to, we're setting the next node. So we're setting this data field in the node to be null. Now at this point, this is a linked list of size 1. All right, we've got the address of some node, there's data in it, it says the next one's null, so there's just one node in this list. Does anyone have questions about this? Okay. Then what if we want more nodes? Well, we do another malloc. And when we do the malloc, it asks for the chunk of memory and we get some address back. Now, in this case, we've stored the address of this new node in a variable called new node. Right, and then we can take that address and go to it and set the data inside, and I've done that to 99. But what do I want to set this next field to be? So in this example, we're adding this node to the start of the list. So I want new node to actually end up being the first node. I want the node after it to be this node I've already got in the list. Okay, so I'm trying to connect this new node to what's already in the list, but have the new node at the start. What's the address of this node that's already in the list? Well, in this case, it's 0x88. Actually, I'll get my pen. Why am I drawing with my mouse? That's what we want in there. But what's the variable that has this value in it? Head, yeah. So we're saying new node next equals head. So what it's actually doing is copying that address into here. That's what it's actually doing. But we can think of it as the new node is now pointing to whatever's already in that list. It's pointing to the beginning of that list. And if there are lots of other nodes in there, they'd still be in there too. We're just adding this one to the beginning. Okay, any questions about that? Oh, and we can see it on the next slide where I've actually done it, I think. Oh, but right now, what have I forgotten to do? Yeah, I've forgotten to update head. So head is not pointing to the beginning of the list now, which would be bad because now if we wanted to print out our list and we started printing from head, we're not including that first element. We need to update the beginning of our list. So anytime we're taking something off the list at the beginning, adding something to the list at the beginning, we need to make sure our head variable's updated and it knows that that new node exists and is connected to the list now. So to do that, that's quite easy. We just say head equals new node. So what that's doing in the code is it's copying this address into this head variable, but you just think of it, well, now that new node is the head of the list. The head of the list is now that new node. Yep.
Are these nodes two separate things, or is the second node related to the first node?
They're not related in that they're in a completely separate space of memory, and we're linking them together just by knowing the address. So yeah, it's kind of like a scavenger hunt. So when I go the head, this variable, oh, if I go back, this variable here has the address of the first node. This node's somewhere in the heap. Okay, now this node knows the address of this other node. That's somewhere completely different in the heap. So, you know, I guess it's a bit like knowing the address of a person, going to their house and they tell you the address of someone else, going to their house. Yeah. I don't know that anyone's ever really done that in real life, but that's all I could think of. Now, if we want to package that up nicely, because we'll be creating lots of nodes, we can make a function, which we did already. So basically, this function is just responsible for doing the malloc for us, so we don't have to do that again and again. Now, it's very good practice to just check that our malloc works. In most of our the stuff we're doing, which is quite small, there's probably going to be enough memory for our mallocs to always work. But actually, maybe sometimes we'll have a bug and actually be doing something silly with malloc in a loop. So it's just always best to check that malloc did work. Otherwise, we would, if it didn't work, it returns null, and we would then be trying to say null arrow data. That would crash our program. All right, so assuming we get our malloc, we're just mallocing that, and we're just setting the data field so that when you're using it, you can pass in, I want this node to have, say, 9 in it, and we go and set that in here. I want the next node to be whatever it is, and we just go and set that in there. And then we return the new node. So this is just doing what we saw before, but we've packaged it into a nice function. All right. So we did that, adding nodes to the beginning of the list. And then we looked at how we could traverse a list, which means go from the first node one by one until we're finished. What does finished mean? I guess it depends. If you were printing the list, you'd want to go right to the end. Sometimes, you know, you might be trying to search for something. Once you've found it, you might not care about continuing on. But generally speaking, it's just going through systematically one by one through the list. How do we do that? Now, we always need to make sure we've got a pointer to the head. So we've got to be careful if we're moving head around to traverse through the list, if that was our only pointer to the beginning. So typically, we make another variable. It doesn't have to be called current, but typically it's called something like current or car, which is meaningful. So we set it to the beginning, and to move it to the next one, so right now, current has the address 28. Why? Because that's the address of the first node in the list. Once we finish looking at this first node, we want to move it to the next node. So we want to move it to here. So we don't want that address in there anymore. We want the address of the next node, which we can find in here, right? This is current, this node is current. This is current arrow data. This is current arrow next. So to do this, we say, current equals head. We want to move it along. We say current equals current arrow next. Okay, if we do that again, if we say current equals current arrow next, we'll be saying current equals 60, which will have the effect of moving it along to point here. So this is a standard thing of moving a pointer from one linked list node to another. Okay. Any questions? Oh, we're still going. Now, when do we stop? If we really want to go through every node in the list, we don't want to stop until we're at null, right? We've gone through all of these. We keep going, we're at null. There's nowhere else to go. We stop. So this is how we wrote, using all of that, this is how we wrote print list. We've got a current, which we put at the head or the beginning of the list. We keep going until current is equal to, we keep going while current is equal to null. I mean, while it's not equal to null, oh my goodness. We stop when current is equal to null. For each node, we're printing out the data inside it, and we're saying current equals current arrow next. So that's basically what we did here. But at each point, before we move to the next one, we're just printing it out. So you can add whatever code in here that you wanted to do for every node. Oops, and this will be sort of a general pattern, just like, oh, I've done the wrong thing here. It'll be a general pattern just like when you do a while loop or a for loop going through an array, you'll tend to do it again and again and again, this kind of pattern. All right. So any questions before we now do something different? Anything that's making you completely confused instead of just slightly confused? Yep.
For link list, when you do like the node to another node, is every single node like a new like malloc?
Yeah, every single node is a whole struct that's been mallocked.
Okay.
And we malloc it because we don't know how many of these nodes we're going to need, and we can malloc them as we need them. And we can also then use functions and pass things through functions, create nodes in functions, and not worry about, is that function that I created it in going to end, and am I going to lose that node, etc. All right, so we've looked at inserting at the head of the list, and I did it in more detail in the last lecture. We could also have a situation where we want to insert just somewhere in the middle of the list. We'll do that later. Sometimes we want to insert right at the end of the list, which we can call the tail of the list. So that's what we're going to do now, this special case, inserting at the end of the list. So the first step to insert at the end of the list is to find the last node. Once we find the last node, then we can connect our new node that we malloc to that last node. But we can't do that until we find that last node. How do we find it? How can we find the last node, do you think? Well, yeah, so we have to have some kind of, yeah? Oh, so we had a suggestion to have a while loop while current arrow next is not equal to null. Actually, that's a really good suggestion. But, and that's exactly what we're going to do. But the main thing is we have to definitely start at the beginning and keep looking along. We have to do some kind of traversal. So when we were printing the list, our condition was to stop when we got to null. But note, if we do that, we've gone past the last element in the list. Like we've gone past it. So we don't want to do it quite like that. We actually want to stop when current is here. We want to stop one earlier. And we know that we're here because if we look at the next node in this particular node, if we look at the next address, it's null. So our condition, in this case, because we want to stop one, like right at the last node, but not when we've gone past the end of it, we do it like this. Current arrow next equals null. And then we can stop here. Is everyone sort of happy with that? Okay, if we go past it, we can't connect it up. All right, now once we've done that, imagine I want to malloc, or I want to connect a node with the value, I don't know, I think I've got it drawn on the slide. Imagine I want the value 9 connected to this. I would do a malloc, create a new node, put the 9 in it, put null because this is going to be at the end of the list, but now I've got to connect it up to this list, right? How am I going to connect this new node, called new node, to this list? Yeah, so we had current arrow next equals new node. So imagine this new node is at address, I don't know, 52. We're saying current arrow next. Remember, current arrow next is this field here. We don't want it to be null anymore. We want it to have the address of this new node in it, which means it's connected up to that. Okay? So you think of it at a higher level often. You're not writing these addresses down. You think the next one after the current one is the new one. So you say current next equals new node. All right. Oh, and I've got a nicer drawing here. This is my new node, my fake address, and the value 5. I need to connect these things up. I say current arrow next equals new node. Okay, and this field in here has been changed. So now the one after this in the list is this new node. Okay, any questions? Does that make sense? All right, let's try this in code. Unless you've got any questions. All right. Okay, insert at tail. Now, what did I just say? Okay, we've got, I'm just going to call it car. So I've got a pointer. No, I'll call it current. I'll call it current. I can type those extra few letters in. I've got current pointing to the head of my list. And I'm just going to draw a list. This is how I usually draw lists. Oh. Without all those sort of fake details. Actually, that's too big. Oh, dear. All right. That's how I often draw a linked list. Anyway, so I've got current, and right now current is equal to head. It's pointing to the head of the list. Okay. Now we're going to do that loop that we discussed. We're going to say while current is not equal, no, that wasn't it. Current next is not equal to null. Right, we want to stop at that last node. We want it to get to here. We don't want it to get to null. We want it to stop here when the next one's null. And by the way, this code is going to have a bug in it. And I know, so it's okay. If you're thinking, hang on. All right, and we want to just say current equals current arrow next. This is going to move current along until it gets to here. All right. Now, once we've done that, and actually even before we've done that, I could have made my variable new node, struct node, new node equals malloc size of struct node. And be very careful when you're doing the size of. Yes. When we'll have a break in. Do you want to have a break now?
As long as it's before 11:48. Any time is good. You can keep going.
I'll make this node, then so just when you're mallocing a node, make sure you malloc the size of the struct. Don't put a star in there. Otherwise, that's the difference between saying the size of, an address you've written down in your address book versus the house. It's not the same size. So be careful you put the size of the struct, not the size. Don't put this star in or anything like that. Don't do that. All right. So I'm making my new node. I'm putting the data in. In fact, I could have just called my function create node. That would have been easier. And I'm going to make it null. So my new node, I'm putting 9 in there. I've got new node. Okay. And I haven't done error checking. I'm just leaving it for now, assuming my malloc worked. Okay. Now I want to connect it to the end, right? I want to connect current to this new node here. Just like I did in my much nicer diagram in the slide. So to do that, I said current, basically the next one after current should now be this new node, all right? So that's just exactly what we went through on the slide. Any questions? Yep.
Why are we not using pointer here? Current next equals to new.
Oh, because this is just the variable. So here, new node is a pointer, and that contains an address. If I put a star here, I'm trying to go to that address and get information out. If I just put new node like that, I'm copying the address in. Okay. Okay. I think we've got to go for a break. When we get, no, I'll just quickly run it. So let's compile this. Linked list insertion, linked list insertion. I haven't caught it. Let's go to a break. When we come back, I'll actually change the main function to use this function. We'll test it, we'll see what's wrong with it, and we'll fix it. Because there's something wrong with the stream, and apparently we've got to go for a break now. Okay, that's why. So let's come back at what time, guys? We don't know.
12.
Let's make it 12. We come back at 12. All right. I know I'm leaving you hanging right now. You're desperate to find out how this function works. Welcome back from the break, everyone. Let's get back to this problem. So I was trying to insert at the tail of the list. We had done a traversal. I'll go through the slides, which are a bit nicer than my drawing. We'll take that away. We had, found the tail by going through until we got to current next equals null, because that's the last node. We created a new node, and I used the create node function. And then we connected this last node that current's pointing to up to the new node by saying current next equals new node. Okay, and that's what I've just done in the code. And of course, the drawing I did myself looks a bit like this, but it's the same thing. Now, to see if it works, we've got to actually use the function right in the main, which I didn't do. So in this, I've got a list that I made before with last week, adding it to the beginning. Here I'm going to make a second list, and I'm just going to say insert at tail. This list is called head 2, and I'm just passing in data from this for loop. So I'm just passing in I. So this is going to create a list, and it's going to add 0, then 1, then 2, then 3 to the end of the list. Like that's what we're aiming to do. Now let's compile it. Oh no. Oh, here we go. Let's compile it and run it. Oh, so it's crashed. So it was fine in the code we did before, but now we're trying to insert elements into this list. This is the code we've just written, and it's crashing. Now, why would it be crashing? Can anyone? Yeah?
Because it's not updating the value
Ah, so it's not updating the value of what? Yeah, do you mean up here? Well, no, that's correct. That is one. There's more than one problem. You found one problem. The other problem is when we start this, the first time we call this function, we're passing in null. The first time we call this function, we've got an empty list. And actually, you can see that detail in here somewhere. The first time we call insert tail, we've got nothing in our list. We're passing in null as the head of our list. And this is where it's crashing. Now, why would it crash if we pass in null? So right now, our list, the head of it's null. What's going to make it crash? So if head is null, what does current equal on this line? Null. We're saying current equals head. Head's null in this case when we're passing in an empty list. Current's null. What happens if we try and say null arrow next? Because if current's null, that's kind of what we're saying. What happens then? Yeah, it crashes. So anytime you've got a pointer and it's equal to null and you try and dereference it, that's what the arrow does, dereference it. You're trying to go there, go to null and get a value out, your program's going to crash. So we passed in an empty list. An empty list has the head is equal to null because there's no data in it yet. We've set current to have null, there's no data in it yet. And then we say current arrow next, we crash. So this is really common and you're going to be having your programs crash a lot because of this over the next few weeks. So what we have to do is add a special case. Where's my cursor gone? Okay, here it is. So over here, before I've even done this, I'm just going to check if the head of my list is null, this means my list is empty. Then what's going to be, like, what do I do? I'm trying to add a new node to the end of an empty list. Do I have anything to connect it to? Not really. But what's the head of the new list now? Yeah, so now there was nothing in the list, but now I've made a new node, and that's the head of the list. Does everyone agree? So the head of the list was null, there was nothing in the list. I'm trying to add this to the end of the list. I create a new new node. That's now the head of the list. That's the only thing in the list. So if the head is equal to null, I've got an empty list. I can't go and do all this code to find the end of the list or the last node in the list. There's nothing there. It's going to crash. So I can do something like this. And now if I compile this, I've got that special case, and I compile it and run it. It didn't crash, but it didn't really do anything. It didn't print anything out. So it didn't crash. So this part here stopped us from dereferencing our null pointer. But when I go and print my list, oh, I didn't print it. Maybe it is there. I just didn't print it. It's not going to be there though. Let's try it anyway, because yeah, there's nothing there. There's lots of new lines. Yeah, and this was the error that, sorry, I forgot your name actually, that you brought up. We hadn't updated the head of the list. So over here, I've got a variable called head2 in the main on the stack, and it's equal to null. Oops, head2. Right? Does everyone agree? Now, when I call my function insert at tail, I'll be passing in null and say 0 the first time. So let me go down to here. I'm passing that into the function. So my function insert at tail, it's calling it head, but it's getting passed in null and 0, for example. Right? And the data is equal to 0. Now it's going to create a new node, and it will have a new node variable. And again, I'll make up a fake address. And when it's done a malloc in create node, it would have created something on the heap, and it would have put this data in it like this. Right? So in our insert function, I've got a parameter called head. Imagine it's passed in null. I've got the data, it's naught. I've got my new node variable. It's storing the address of this node I've created on the stack. Now in this case, I'm saying, okay, let's make the head equal to null. So, oh, no, I'm not. If the head's equal to null, let's make it to basically point to the new node or be equal to the new node. So I'm changing this in here to have the address that's in new node, which is OXE0. So now head in insert tail is pointing to this new node. All right, is everyone happy? So head in the function insert at tail is pointing to the new node that I've just malloced. Now when this function finishes, all of these variables on the stack don't exist anymore. This malloc node does. It's on the heap. But what does my head2 variable have in it? If you can read it, null. So head2, the original list back in main, doesn't know about any of this. The original list back in main says head2 equals to null. In insert tail, it did all this stuff. It set it all correctly. But back in the main, it still has that original information, head2 equals null, and it's never been modified or updated. So what we have to do is we have to return this data. We have to return it and say, actually, this is what the head of the list is now. And by the way, when we put this star here, we're often putting it right next to the function name, but this is the return type. So now we want this function to return the head of the list. So anytime the head of the list was updated, it can let the main know, right? Please update your information. So it's like if you've got my address and I move, I have to let you know so you can update my address. So this function's updated what the head of the list is. In that case, it needs to let the main function know. So now we've got to return the head at the end. And that's not enough. The function needs to do that, and the function's all good. But then when we call the function, we've got to make sure we're not ignoring that return. So if I just compile it now, I'm returning this, but I've still got nothing because I haven't used the function properly. I have to say head2 equals this. So my function is saying, actually, this is the address of the start of the list now, and I've got to make sure I store that and update the address of the start of the list. So if you don't do all of those pieces, it doesn't work. All right, let's try it. Well, hopefully it does work now, right? It doesn't, oh, it didn't save. Fingers crossed. Yay. And I'm calling print every time so we can see it's growing. We're adding it to the end. But yeah, the thing is, anytime you might be updating the beginning of the list, which we certainly are if we're starting with an empty list, we're always going to be updating it. You've got to make sure your function returns what the head of the list is now. And you've got to make sure you update it. You actually assign it to your local variable. Okay. Any questions about that? Probably, but you don't know where to start. Okay, so that's adding to the tail. We're going to do another example of inserting something into a list. So this time, the slides go through what we just did. Okay, and then it shows you the final thing. So we've looked at inserting at the beginning and the end. Now we want to be able to try inserting somewhere in the middle. So let's just clear our heads and think about this. So if I've got a list and I want to insert somewhere in the middle, I've got to work out where the middle is. Now, the easiest way to start with is to find out, well, what's the size of the list? If I know the size of the list, then I know where the middle is, at least like a counter. So if this list is size 4, which it is, I'm looking for the node at, say, position 2. I want it to be in position 2 once I've inserted it. So if we think of our positions, and remember, this isn't like an array where the computer knows, oh, here's position 0, 1, 2, 3. But we're going to be counting along. And when we count along in our loop, we're going to call this 0, 1. And if our list is size 4, we want our new node to end up at position 2, because then it will be in the middle. So we find the size of the list, we divide by 2. That's the position we want our new node to be. How do we find the size of our list? No, we can't. Size of will tell us the size of one node. C is not going to know how big our list was. Yep. That's right. The answer was we can loop through it until we get to null and count as we go along. So if we haven't kept track of that ourselves already in a variable or something, we can count through the list. Okay, so that's the first step. Before we can insert in the middle, we have to have a way of finding the middle. This is one way. There are other sneaky ways of getting to the middle of a list, but we'll do it like this. So I've got my list length function up here. And I need to write one down here. So this is returning an int. It's called list length. And the input's just going to be some kind of list. Oops, that wasn't very good. Oh, 24T3. Okay. There we go. All right, so again, we're going to do a traversal. So remember, when we have a traversal, we typically, imagine I've got this situation, I've got a list of size 3. I'm going to have some counter that I set to 0. I'm going to have a pointer called current that I set to point to the head. And then every time I go through the loop, I increment my counter. So, you know, I check my while loop, is car equal to null? No, it's not. So I increment my counter to 1 and I move car along. Are we at null? No, I increment my counter, I move car along. Are we at null? No, I increment my counter and move car along. I've got to the end, but now my counter knows that there were 3 nodes. So we're just traversing the list, but just counting the number of times we go through the loop, because that's how many nodes we have. So I'll make a counter, and I'll make a pointer to a node. I'm going to call it car, and I'm going to make it equal to the head. So car is pointing to the head of the list to start with. Now notice, if our list was empty, this function should still work because the condition is car equal to null or not. That's fine. It can say, yeah, it is equal to null. The loop does nothing, and our count is still 0. So that's going to work. But in the loop, every time we find a node that wasn't null, we add it onto our counter. And then we keep doing our traversal by saying car equals car next. Okay. Then at the end, I return my counter. Now, do we think this will work? Does anyone have any questions? Do you want me to go through that code again, explaining what happens? Do you want to do a poll? Can you guys do a poll to see who wants me to go through list length again? Because, yeah, it's important to get this basic thing before we move on to something like the rest of it, inserting in the middle. Yep, question?
Do we finish this far with, like, we still have to go for middle?
Sorry?
Is that the end of the middle part?
No, we haven't even started the middle. We haven't started inserting in the middle, but the first step is to find a function, to write a function that can find the length of the list, because then we're going to use that in insert middle. But before we do that, we want to make sure that this function works and is correct. So we should probably test it out. So while I'm waiting for that poll, let's just test it out and see if it works. So we've written something to find the length of a list. I'm just going to shove it in here because I'm printing out lots of lists. Let's print out how big they are before we print them out. Okay. Yep.
If the number H size of the linked list is supposed forward, then what do we consider as the middle?
Okay, so we've got a good question about when we insert in the middle. Yeah, sometimes there's no middle. If you've got an even number of elements in a list, there's no exact middle. So typically we might take just one of those middle items. So if it's the middle to the left or something, that's fine, if you don't care either way. Yep. So with this, let's just check if this length of a list works. Okay, so it's saying that the size of this list is 1, the size of this list is 2, the size of this list is 3, the size of this list is 10. Okay, does it work? Let's just double check. Oops, that's not what I wanted. Yep. So I'm just testing it, and then I'll go through the code again of list length. We just want to check that it did work. Yep, size 0 if we had an empty list. All right. is everyone clear about what this is actually doing, this function? Just working out how many elements we have in our list. Okay, do you have a question? No, okay. So I'm just calling it repeatedly. We had a list with nothing in it. It said size 0, this one, size 1, size 2. Let's go through it again. Let's go through the code. And I might actually draw fake addresses. So imagine I've got a list. Let's start with the basic case. Imagine I've got a list and it says head equals null. My counter is going to end up being, my counter gets set at 0. My car, which is another variable, it's equal to head, car will be equal to null. So this is the null case. We always need to check this works for things. We now say, is car not equal to null? Car is equal to null. So we're not going to go through this loop at all, and we're going to return 0. So for the base case, or the simple case, where we've got nothing in our list is going to be null, car is going to be null, and we're going to return 0. Is everyone happy with that? Okay. Now what if the list isn't null? That's the problem. So imagine the list isn't null. And I've got head, I'll draw it over here. And I've got some list over here. That'll do. Now imagine our addresses are like that. Oop. Oh dear. All right, so our list is living at address OXF0. So this is the head of our list. This node here is connected to this node here, so its next field would be E4. This node here is connected to this one, so it would be F4. This one has a null. Okay, so that's our list. Now we've got a counter, and our counter is equal to 0. All right, so we're going to make a variable called car. And car, to start with, equals head. So it's going to have this same address that head does. It's pointing to exactly the same place as head is. So is everyone happy with this line here, what car equals head does? Because that's really important. Car and head are both pointing to the first node in the list. They both hold the address of the first node in the list. Any questions about that? Does that make sense? Okay, so now we get to the loop and we're asking, is car equal to null? Is it not equal to null? Well, if I look at car, it's not equal to null. Car is actually pointing to a node. It's not equal to null. So now we increment our counter. So now our counter is equal to 1. Oops. But I update car. I say car equals car next. Car right now is pointing to this first node. We want to move it along to point to the next node. But car next, this is our current node here. Oops. This is our current node here. Oh goodness, me and this pen. This is our current node here. This is current next. This is the field current next, or car next. That's the address of the next node. We want to move car along to the next node, so we say car equals car next. So this has the effect of changing this address to now have this OXE4. So this was car next. We're getting that out and putting it in car. Now this means car has moved along and is pointing to the next node. Okay. Now we check again. Is car equal to null? No, it's got the address of some node. So we increment our counter. Our counter is now equal to 2. Is that right? What was it before? And we want to move car along. So we say car equals car next. So it's going to update this to the address that's in here, which if anyone can read it other than me, says OX F4. So now car contains the address of the next element. Oh dear. The next element, which is over here. When we get to here, is car equal to null? No, it's still pointing to a node. It doesn't have the value null in it. So it goes through the loop again. We increment our counter. It's 3. And we say car equals car next. Now at this point, what's the value of car next? Well, car is pointing to this node. So the next field of this node is equal to null. So right now, car gets set to null. It's not pointing to any node in the list. It's done. It's gotten from the beginning to the end. And our counter's at 3. And we return our counter of 3. Okay? So the idea is we're doing a traversal, starting at the end, saying car equals car next until we get to null. But we're incrementing our counter each time. And that's actually counting how many nodes we traversed through. Okay. Any questions? All right. Let's move on. Now we know that we've got a way to find the length of a list. We want to use that to insert into the middle of the list. Oh, that's not what I want to call it. Insert middle. Okay. All right. So, yeah, in this case, we would want our new node to be at position 2. Let's assume we're calling this position 0, 1, 2, 3. We want to insert a new node that will become position 2, right? How do we do that? Well, we can find the size of our list to work that out, and then we want to keep going. We want to traverse through the list until we get to here. So we're calling this position 0, position 1. We want our new node to be at position 2, and for this to become position 3 and 4. So we want our new node in here. We need to stop before we get to that position, because we need to be able to connect this node that will end up being before it to it. So we don't want to go past that node. We want to stop just before it. So we're stopping at -1, that -1. Once we do that, it's just a matter of connecting things up. So we'll probably have a pointer called current that stops when it gets to here. And we need to connect 2 things up, actually. This will be our new node. Right, and it'll have some value in there. We want to make the next equal to this one that's going to be after it. What would this be called? So current is this node here. What's this node? Current next, yeah, current next. So we would say we'd want this address 60, which we would get from current next. So the one after the current one is the next one we want after our new node. Okay, then we say, well, now actually the next one after current has to change. The next one after current should now be this new node. So we just have to find the right position, create our node, and then just make sure we get these pointers right, but connect these two pointers to connect it in. So let's just see it on the slide. So again, I've got some kind of pointer called current, usually starting at the head. And again, I'm using this concept of a counter to work out when I'm one before halfway through the list kind of thing. And I keep going until I get sort of midway and the counter's saying, yep, you're at this one before what would be the midpoint. And this is all this loop is doing, counting if we're up to just one before halfway. And like you said, depending on whether we've got an even size or an odd list, halfway, you know, there might be two middles. And as long as we're in one of the middles, we're good. Now we want to connect our new node. It should come after the current node, but before current next. So when we make our new node, we would do it something like this. Now we want to connect this first. We want to connect the new node to current next. We want to put this link in first. Then we want to change this other link. We say current next equals new node. Now if we did it the other way, if I changed this link first and said, okay, current next equals new node. What would be wrong with doing that? Well, so it's saying current next equals new node. Yeah. So what we've done is, I think what you're saying is right. She said it would end up with the address of itself if we just said, if we use the same code. But what we've done is we've lost the rest of this list. There's no variable at this point that has that address of that, you know, OX60. It's gone. We've lost it. We've broken the chain and we've lost that address. Yep.
Why can't we let OX60 below the OX50? So it's not just connected.
If we did what?
If I took the OX60 below the OX50, so like this
Yeah, so what we want to do is, we want to put this address in here to connect it, but we've lost that address. We can see it on the picture as humans, but in our program, there's no variable anymore that stores that. The variable that stored it was here. So if we overwrite this, we no longer have this in any variable, right? And we've lost it. It's like losing someone's address. It's, unless you go and knock on every single door, look for them, you know, you're not going to find them. So we've got to do it in the right order, and that's often the case when we're working with linked lists, that we've got to make sure we set things in the right order so we don't overwrite something that we need. So we set this first, then we set this. We're saying the next node after new node is, you know, the next node after the current node. Let's go back to here. So this was the current node. This is the next one after the current node. That's going to be the next one after the new node. Then we say the next one after the current node is now going to be the new node. And that slots it in exactly where we want. Now, if we just code all of this up, okay, let's try it. So we want to find the middle index or the middle position. So I'm going to use the code I've already written, and I've already tested that code somewhat thoroughly. We're finding the middle. Yeah, so we can divide that by 2, and we're using integer division. Let's let integer division decide what middle is for an even number. It'll be the smaller. All right, so now I've got a current. Maybe I should keep writing the whole word so it matches the slides. I'm starting the current at the end. Now, I said in the thing that the condition we're looking for Oh, I need a counter. And I basically know where I want to stop. I want to stop while counter is less than middle minus 1. Middle's the size on 2. I want to stop 1 before I get to the middle because I need to have the node before it to connect it to. While that's happening, I just keep moving along, incrementing my counter, saying current next, current equals current next. So here, this is what I was showing you before. I'll go back. Where I was doing this loop, I initialized my current and my counter, and then I was just moving it along while counter was less than that size on 2 minus 1. So I was finding that node that I want to insert the new node after. Now, once I did that, we wanted to create the new node, and then we wanted to connect it up. So let's try that part. So actually, let's make the new node. No matter what, I'm making the new node. So let's do it up here. Struct node, new node. I'll use my create node function, passing in my data. Oops. For now, I'm just going to set the value to null. I don't really know what this next node value is going to be, but I don't know what that is yet. But for now, I'm initializing it to null until I've worked that out. All right, so when I get to the end, I'm going to do this part where I say this new node next equals current next. Now, does anyone have any questions about this line of code here? How this connects this new node to this particular node here? All right. So it's saying that the next one after this node is the next one after this current node. Okay. So I'm going to say new node next equals current next. So I've put that connection in, right? Now I want to put this connection in and connect this one that's current. I want to connect it to this new node as well. And to do that, I'm saying current next equals new node. So I'm updating this next link to be connecting to the new node. Now, that's it, right? We'll see. Now, to test this, let's actually create the same list that we had in the lecture slides, so we can easily see if we've got it correct. I'm going to make a new list called excitingly head 3. It's our third list. I'm going to just create a list first. I'm going to say head 3 equals insert at tail. And I'm just going to make our original list from the slide. I'm going to put 13, then 17, then 42, then 5. And before I get too carried away, I'm going to print it out just to check I haven't done anything wrong. Okay. Yeah, so down the bottom, I've got this list here. With 13, I might just put something to remind us what we're doing. There we go. So I've got, one more thing. Sorry. Okay, I've got this list. And just because we've already done the diagrams, I wanted it the same. And I'm going to insert 9 into this list at the middle. So I'm going to say insert, head 3 equals insert. Okay, I haven't got a prototype, I don't think. That's better. Okay, let's try again. Insert middle. So I'm passing in my current list, which has some data in there actually. And then I'm going to say insert 9 into the middle of this list. Then I'm going to print it. Now we want to see if this works, obviously. Does it work? Yeah. So this was my original list. And I've inserted 9. Is 9 in the middle? Yeah, so that seems to work. What if I do the other case? Let's insert another node. See what happens when we don't have an exact middle, right? If I have one more node, it's going to be an even size list. There's no real middle, but we want it to be one of those middle nodes. Yep, the 23 came in here, which we're calling the middle. That's fine. Now, who thinks this works completely? Do you have a question? Is there anything we should test that I haven't tested? Negative numbers? I think in this case, the negative number will just exist. Like if let's try it, I put a -9 in here. It should still work because nothing is due to the order of the actual data we're storing. But in some cases, that would make a big difference. Like if we're inserting it in ascending or descending order. Yeah, we haven't tested because I created a list first. What if we've got nothing in our list? Let's create another list. We should always test for an empty list because this is what can break us. And usually we do start off with empty lists. Yeah, we've got a problem. So it seemed to work fine. We had lists, we were trying to insert in the middle. What if the list we're inserting in the middle of has nothing in it and the head is null? Well, let's go down. It's actually telling us, it's telling us over here that it's on this line here. So yeah, we're having this case where we would be saying null, arrow next. So we need a special case. So basically, if the head is equal to null, which is kind of the same as maybe there might be another situation where the middle is equal to 0. Okay, I'll put both in. So basically, if you need to insert it at the beginning of the list, let's put it here. And all right, well, maybe let's just do this case. If head is equal to null, let's just return the new node and say that's the head, right? Or if this is clearer, we could do this. Is this going to solve our problem? Okay, nothing crashed. Is it completely working? I don't think it is. We are running out of time. So let's just try it. Let's do another loop. A loop allows us to try it at lots of different sizes. So I'm going to say head 4 equals insert middle So this, by doing it like this, we're testing it with a size 0 list, then a size 1 list, then a size 2 list. Because maybe there's something weird that happens with a size 1 list. That seems to work, right? Okay. All right, I think that's all we've got time for today, which is probably enough. But does anyone have any questions about this? And one of the main sort of messages is always check for a null empty list. Next lecture, we'll recap this insert middle and do a similar function called insert at index, and then we'll start looking at deletion. Okay. All right, thanks everyone. See you on Thursday.